Okay, so at the end of yesterday's class, we were starting an electrostatic electricity review preview. And I apologize to both groups. There's some of you that have just done it and you're like, in physics? And it's like, seriously, do we have to sit through this again? And some of you who haven't seen it before and you're like, oh no, do I really need to know this? So just bear with me. We're going to go through this because it'll be helpful when we get to magnetism. There's an amazing similarity between gravity, electricity, and magnetism. That's why, even though I was calling this an electrostatic and electricity review yesterday, why I started with the equation Fg is equal to gmm over r squared, because I want you to see the similarities. So this Fg is equal to gmm over r squared is the real equation for the force of gravity, brought to us by Sir Isaac Newton, where m1 and m2 are the masses of the two objects. R is the distance from the center of one object to the center of the other. So between centers. Now, we tend to think of gravity as something that the Earth puts on us, or the moon, or the sun, but really every one of us is exerting a gravitational force of attraction on every other object in the universe. This is known as the universal law of gravitation. It's Newton's universal law of gravitation. Okay, universal means does not matter where you are in the universe, this law works. And so I am exerting a gravitational force of attraction even now on this snow day on every one of you. And you are exerting it on everybody, like people in England, in Africa, in Australia, in South Korea, no matter where you go, in China, in Mexico, no matter where people are in the world or buildings are in the world, you're exerting a gravitational force of attraction on them, where one of those m's is your mass, the other m is their mass, and this r is the distance between the centers of those two objects. Now, if it's me and you, center to center is not going to be very different from measuring from the outside of our tummies to the outside of the other tummy. But if we're talking about the Earth and the Sun, the r will be very different if we measure from the center of the Earth or from the outside edge of the Earth. So we always say center to center. And then capital G is the universal constant, okay? And we attribute it to Newton, but he didn't really get the value of it. He just knew it existed. It is equal to 6.6... I'm going to get it mixed up because I'm already thinking Science 12.2. So as I look it up to make sure I'm not going to screw it up here, there are two constants you're going to use in this course, and they're too close. Okay, it is 7.3. They're too close to each other in my head. The other one is 6.626, and I always have to pause after the 6 to say which one am I about to write. So 6.673 times 10 to the negative 11 Newton meters squared per kilogram squared is this constant. Okay, and then Fg is the gravitational force of attraction. One object is always pulling the other object in. You never have to worry about which way is the Earth going to pull you. Okay, so we could figure this out for two of you. If we were in the classroom, I would take one of your masses and a second mass. We'd measure the distance center to center, and we would figure out your Fg. So let's just say like if mg, or m was like 40 kilograms for one of you, which is very tiny, and the other one of you 50 kilograms. And if you were like a meter apart, we could figure out this value. So you would do 6.673 to the negative 11 times the 40 kilograms times the 50 kilograms divided by the 1 meter squared, and I hope you didn't just punch that in your calculator. And you will get an Fg of so Fg would end up equaling 1.3346 to the negative 7 newtons. That is minusculely tiny. So we're exerting this force on each other, but even when we're only 1 meter apart, it's so tiny we don't notice it. So those people that are in Australia and South Korea and China and Mexico, they're definitely not going to feel our force because the 1 meter is even bigger. Okay, so for us, we're exerting this force, but it's really tiny. But if we go to the Earth, like the mass of the Earth is 5.98 times 10 to the 24th kilograms. That's significantly larger than our masses. So when we put that in there, it makes a big difference. If we were to use that as one mass and the other mass 50 kilograms, and if you're standing on the surface of the Earth, the radius of the Earth, and again, I've lost all the constants in my head. It's 6.38 times 10 to the 6 meters. So if we were to fill these three numbers into this equation and find the FG with them, so in your calculator, 6.673 to the negative 11 times 5.98 to the 24 times 50 kilograms times 6.38 to the 6th squared. If we were to do the, I think I missed something because I just got a really huge number. I think I missed the negative on my constant. E to the negative 11 times 50 times 5.98 to the 24th divided by 6.38 to the 6th squared. You get 490.17. 490.17 newtons, which is a much more reasonable force than the -7. This we can feel. This is the force that about the force the Earth is putting on any one of us. It's around 50 kilograms. Okay. Now, if I wanted to, so maybe that's the force on one of you in the class. If I wanted to do it on a different one of you, I just have to change this number. So think back to Newton's time. They were multiplying these big, huge numbers by hand, and they were like, oh man, this is killing us. And the only thing we're changing is one of the masses, because the G, the M, and the R squared are staying the same as long as you're at or near the surface of the Earth. So they were like, couldn't we replace these three things, this G, M over R squared, with a constant? And so if you calculate this for using the mass of the Earth and the radius of the Earth, using this number and the G, you get a number amazingly close, and test it out, amazingly close to 9.81 meters per second squared. This is really our little g, which is what makes the equation that we learned in grade 11 physics, F equals mg. We've just replaced these three, which are constants as long as we're at or near the surface of the Earth, with little g. This little g then is called, we called it all during grade 11 physics, the acceleration due to gravity. It really has another name though. It's also called the gravitational field strength. Gravitational field strength. And to understand that, I need to tell you what a field is. So a field is an area around an object, whether that object is you or the Earth. Both of you have an area around yourselves where if another object with mass enters into that area, it's going to feel this pull. It's going to feel this force that we calculated, be it to the -7 or be it 490. It's going to feel this force, this pull towards you. So a gravitational field is the area around an object where another object experiences the pull of gravity. If you think about the Earth, you know you experience a pull of gravity. That's why you fall towards the Earth. If you put on your little rocket pack and went zooming up into the air, then the pull would get less and less and less because the air is getting tinier. So this gravitational pull would be getting less. The gravitational field, dependent on the R, and it's on the bottom, would be getting less. Okay, all of that to say there's also an electric field around any charged particle. Okay, so we're now going to go to electric fields and electric force. And it's really called electrostatic force. And we're going to run out a video here in a second. Okay, so the electrostatic force looks just like the gravity one, except it's going to be KQQ over r squared instead of g m